Okay, this is the second video in the two video series of conic sections. And in the first video, we talked about parabolas and circles, really just briefly about circles. And I'm looking at the conic section fact sheet. Here's a reminder of what conic sections are. They come from slicing two cones stacked on each other, tip to tip. And so we're going to talk about the ellipse and the hyperbola in this video. Ellipse is kind of like a stretched out circle. Hyperbola looks like two parabolas that are facing away from each other. Maybe they're mad at each other, so they're kind of looking away, and there's usually a gap in between them. So let's take a look at the fact sheet up here. So the nice thing is the equation of an ellipse looks very similar to the equation of a circle. Like last time we got, let me put it right here next to it. You can see x squared, x minus h squared over r squared plus y minus k squared over r squared equals 1. That's the equation of a circle. Okay? Why are you erasing when I write you? Equation of a circle. That's weird. Okay. So you can see how close they are. And the difference is that, so you can see the same x minus h squared and the y minus k squared and equals 1. That's all the same. The difference is I have an a squared there and a b squared there, as opposed to an r squared and r squared. So if you think about a circle being a set of points that are equidistant from a given point, that means the radius is always going to be the same. If you think about an ellipse, it's not the same. Well, here's a picture down here. Actually, what an ellipse is if you pick any point on the ellipse, the distance from, there's 2 points called the focus points, which we'll get into it in a little bit, but basically what happens is there's 2 points sitting here where if you take the distance from this focus point to the given point and the distance from the other focus point to the given point and add them together, that distance will always be the same. So if we take this distance plus that distance, it's going to be the same as this distance plus that distance, which is going to be the same as this distance plus that distance. So that's how a ellipse is formed. But really, you can think of an ellipse as really like a circle, but it's stretched out a certain direction. Okay? And so it's kind of like it has 2 radii, which that's obviously not true because the distance from the center is changing all the time if you're to draw it, right? If you're to go from the center. But basically what the a and the b are in this equation is it's kind of like the radius on the axis. So in this case, the b would be that distance right there from the center to the perpendicular to the ellipse, and so that's my b. Put a pin here, sorry about that. So if we had the center point right here, that would be b. Notice it's b squared underneath here, but the distance would be b, and this distance here would be a. Now the way they describe that in the fact sheet, you can see that it says the length of the major axis is 2a, because you can see that if I was to go through this whole thing here, there's an a there and there's an a there, so that would be 2a. So that's what they're trying to tell you is the length of the major axis is 2a. Because the distance from the center to one edge plus the center to the other edge would be 2a. Okay? And then likewise, the length of the minor axis would be from b, would be b plus b, so that would be 2b. And that's what it's saying there. Now, just to be clear, an ellipse does not have to look this way. An ellipse can look this way. It can be long the other direction. And notice that's what this is talking about down here. Notice in this case, the a is underneath the y, and the b is underneath the x, because what they're establishing up here is a is always bigger than b, just so we're clear on what a and b are. So notice that they're saying just think of a as the bigger number between a and b. And so notice in this case the bigger number is underneath x. That's why it's longer in the x direction. Here the bigger number is underneath y, so that would make it longer in the y direction, so it looks something like that. Okay? So that's ellipses. Basically, you draw them kind of like circles. You use the h and the k to find the center point, and then you use the a and the b to get the 4 points. Just like, remember when we did the circle, we got the center point, and then we use the radius to find this point, this point, this point, and that point. Well, we're going to do the same thing with the ellipse, only these 2 points will be determined by one number, and these 2 points will be determined by a different number. Okay? So let's hop over to my graph again real quick, my graph paper. And let's say we have an equation like x minus 2 squared over 9 plus y minus 3 squared over 4 equals 1. So this is an ellipse. How do we know it's ellipse? We can tell right away it's ellipse because it's something squared plus something squared equals 1, and the numbers underneath are different. If this would have been 9 and 9, then we'd know it's a circle. But because it's 9 and 4, we know it's an ellipse. Okay, so if I wanted to graph this, I would cruise down here, draw my xy axis, go over 2, up 1, 2, 3, and put a dot. That's the center of my ellipse. And in this case, the number underneath x is bigger, which means we know it's going to be longer in the horizontal direction and shorter in the vertical direction. And so the length, so the major axis is going to be in the horizontal direction. So we know the major axis is, so 9 is of course the same thing as 3 squared. So we know the major axis is 6 units long. Or we could say the distance from the center to one vertice is 3. And the center from the distance from the center to the other vertice is also 3. So that would give me my 2 vertices. And then if I use this 4 over here, this is saying if you go up and down, you're going to go 2 away. So I'd go up 2 and put a dot, go down 2 and put a dot. Again, why is it 2? Because 4 is equal to 2 squared, just like 9 is equal to 3 squared. Okay? So then we could try to be smooth and curvy, we could draw a cute ellipse. Okay? So that's an ellipse. Again, they're pretty straightforward. If you just keep in mind, this is actually, a good way to think of it is instead of calling a ellipse a stretched out circle, a better way to think of it is a circle is an ellipse whose axes are the same length. Because notice if we had, like I said, if we had 9 there and 9 there, this would just be a circle because we'd be going like that. Right? That's really kind of a good way to think of it, is a circle is just an ellipse with both the major and minor axis. Well, they don't have a major and minor axis because they're both the same length. So in that vocabulary, the major axis is just the longer axis. So here's the major axis, and there's the minor axis. Okay? So there's an example of ellipse. Now, going back to the focus points, you could possibly picture, let's draw here. You could possibly picture a point somewhere about in there and a point somewhere about in there. That is there are these things called the focus points, and that's how you generate an ellipse, is by every point on the ellipse. If you measure the distance from one focus point and the measure to the other focus point, that distance stays the same no matter where I'm at on. So if I go over here, then that distance plus that distance is equal to these two. If I go over here, that distance splits that distance. So that's how we know where the focus point is. So the thing you need to know about the focus points, let's hop back over to the fact sheet again. So notice this other information here. It says the distance between the center and either focus is c. So if you look at this drawing once again, if I go to the center of this ellipse, there's a distance from there to there. That would be c. And of course, if you go the other direction, that would also be c. And what is c? Well, here's the relationship. C squared is equal to a squared minus b squared. It looks almost like the Pythagorean theorem, but it's not. It's c squared equals a squared minus b squared. Notice that it's a squared minus b squared because we want the bigger number, because we don't want it to be negative, right? So if I know a and b, then I can find c, which is the distance to the focus point. Now, sometimes we don't care, because if we've already got the graph, we might not care where the focus point. But let's say in this case we're interested. Where is the focus point? Well, we know the distance, c, so that distance right there, squared is going to be equal to 9 minus 4, because that's my a squared and that's my b squared, right? So that means that c squared is equal to 5, which means c is equal to the square root of 5. And normally when you're solving an equation like this, you'd say plus or minus the square root of 5, but we're talking about a distance, so we just want the positive. So that means that this distance right here would be the square root of 5. And that distance right there would be the square root of 5. So if I ask you in this case, I'm going to grab a more different color. If we were to make a list of what we know here, where's the center of this ellipse? Well, that's located at 2, 3. And where is the major vertices? That would be at, let's see, what, 2 plus 3 is 5, 3, and negative 1, 3. How about the minor vertices? The minor vertices would be at 2, 5 and 2, 1. And what about the focus points? So the focus points, or the plural, that would be foci, just so you can be cool. The foci would be located, well, we know it's square root of 5 over from the center. So where's the center? 2, 3. So that would be 2 plus the square root of 5, 3, and 2 minus the square root of 5, 3. And of course, you could turn that into decimal if you want, but that's essentially where it lies. So that's all the main players in this graph of this ellipse. Okay? So, of course, if you could go the other way. If I give you a graph, let's say we're looking at a graph like this, and we have an ellipse that's sitting right there. Here's my ellipse. Can you write the equation for this? Well, we know that it's going to look like this, for sure, right? Looks like the vertical distance is from the center is just 1, so that would be 1 squared. And then we can see if we picture a center right there, the distance would be 1, 2, 3, 4, so that would be 16. Got that down. And the location of the center is the point, 3, 3. So I'd put a minus 3 there and a minus 3 there, and boom, I got an equation. That would be the equation to that ellipse. Really that simple. Okay, now here's the fun thing. For hyperbolas, let's take the same equation for a minute, just to be cool, and let's say that instead of a plus, this was a minus. So if you just hop back here real quick, you can see that's the equation of a hyperbola. You got x minus h squared. You see that same players, x minus h squared, y minus k squared. You got an a and a b. Now in this case, though, the a and the, notice it doesn't have that little a is greater than b thing. In this case, the a, it always goes with the still goes with the major axes, but the major axis is determined by the direction that it's going. So in this case, the major axis would be horizontal because the hyperbolas are facing right and left. If it's if the hyperbolas look like this, that would be the major axis is vertical. And so how do you tell which is which? Well, you can see here that this is a horizontal axis because the x is positive. The x term is positive and the y term is negative. This one right here has a vertical, so this would look like that, and this would look like that. Why is this vertical? Because the y term is positive, the term involving y is positive, and the term involving x is negative. So that's what you're looking for in the ellipse, is which one is positive, which one's negative. But you'll see that everything else is kind of the same, kind of. So if I go back over here, like I was saying, let's say that this is a minus instead of plus. So we know right away that it's a hyperbola instead of an ellipse. So it's not going to look like that. But the cool thing is the same points are still true. It looks like it's 4 to the right and left of the center, and 1 up and down from the center. But the difference with when I'm trying to draw a hyperbola is instead of an ellipse, the way I do it is I draw a little box. Now I'm not drawing the hyperbola yet. I'm just drawing something that will help me draw the hyperbola. And when I draw that box, what I'm going to do next is I'm going to draw the diagonals and I'm going to extend them. So the diagonals of that box will look something like this. And like this. And so what those do is they form the asymptotes that determine the shape of the hyperbola. So I'm going to grab a different color here. We'll use blue just so it looks different. And notice that the x term is the positive one, the y term is the negative one. That means that this is a hyperbola that's facing right and left, not up and down. It's right and left because the x is positive. So that means the vertex of one of the parts of the hyperbola is going to be right here, and it's got to stay inside those asymptotes. And the second one's going to be over here. And so you can see that if this is plus, we just have a ellipse, right? But if it's minus, then we draw, it's a hyperbola. It's on the outside. But it's the same points determining where that draw, in one case the points are the major vertices and the minor vertices. In the case of the ellipse, in the case of the hyperbola, the positive one gives me the vertices, and the negative one gives me how wide the box is that determines my asymptotes. Okay, so that's the example of ellipses and hyperbolas. So there's a good practice sheet in the week 3 module that you can begin working on. And let me know if you have any questions, and have fun.